Why are services special? I think that services are special because they create, well, they are involved in embodied and operational emissions. So we do need to think about both sides of the equation. And also they get replaced. So the lifetime might be 10 years, it might be 35 years, with some components getting replaced more regularly. And this is one of those areas where I think, we talk about a change of mindset. There are some big technological challenges in the embodied carbon space, like how do we create low embodied carbon steel, for example. But I think there are some really simple and almost unsexy kind of things that we can do to really tackle this problem straight away. And one of them is extending the life of what we've got. So I think maintenance is an issue that we could probably look at, and yeah, it's a simple win. It is complicated. We will hear a bit more from one of the other presenters about how complicated it is, but a simple air conditioning unit might contain 100 different parts. And those parts will be sourced from many different places, third-party suppliers. The supply chains are complex. They're also dynamic. So a part might come from a different factory from 1 month to the next. That makes things complicated because we're trying to measure how much embodied carbon is in the different elements of a building. So if it's changing every month and it's having a material impact on the amount of embodied carbon, that's going to make it tricky to create an environmental product declaration. And it's also a challenge because a lot of people are trying to tackle this problem at the same time. I think Hudson sort of mentioned the need for coordination. Ideally, we want one system that we can all rely on that's trustworthy, rather than having a bunch of different systems and we're not sure which one to use. So I've tried to explain why it's a little bit complicated, but I think there's also some really good stuff going on. EPDs, the database of EPDs is growing. We do have in the building services space another methodology called TM65, which is sort of an interim methodology. It doesn't go the whole way that the EPD does, but it allows us to measure embodied carbon in building services. And we're also very excited that in June this year, we're going to see the release of the Neighbours embodied carbon tool, which is going to bring in a bit of building services. Systems like Green Star already incorporate upfront carbon. And I guess we are seeing the ask for lower embodied carbon products coming down the line from head contractors and also, as Hudson mentioned, government. And talking to people who are working in this area overseas in the US, we're hearing about the big tech firms really driving change and sort of setting up their contracts so that when they ask for equipment, they're saying, look, you might not have an EPD for this product right now. That's okay. We understand it takes time, and we'll purchase it from you, but on the condition that in a year's time, in 18 months' time, you do have the EPD. And if you don't, then we're going to go to a different supplier. So I guess what we're seeing is that all the different parts of the supply chain are getting involved in this problem and trying to work together. And I guess that's where our panelists come in. So I might actually throw over to Sydney. Is that right? Yeah? Okay. We are going to hear from Jennifer Elias at
Atelier 10.
Yeah, thanks. I'll hand it over.
Great. Thank you. Thank you, Mark. Now, look, we've got over 500 registered attendees for this. Alexi's been whispering in my ear, 260 online, and then all of the people in the 4 offices. So clearly building services is fascinating and important. And to tell us more, associate at Atelier 10, as well as involved with the Chartered Institute of Building Services Engineers, or CISBE, New South Wales. Jen, can I ask you to take over?
Thanks very much, Hudson. Okay, so if we scroll on maybe a couple of slides, brilliant. So look, I pitched this presentation to the MECLA team, and I really wasn't sure what their response was going to be. This is quite a complex presentation, and it really only kind of tangentially touches building services. So I pitched it. Jeff says, as he often did, I think that's a great idea. He really wanted me to hit 2 key points, which will come up in a second. And that's really the 2 things here that, look, this is a complex topic. There are some uncertainties that we need to deal with and need to grapple with, but we really want to be energised to move beyond those. And then the second one, that we do really need to think deeply as custodians of the world's resources about how and where we invest those into buildings. So on that note, I'll start on the embodied carbon of building services. So for this presentation, I've drawn on some EPD data from Daikin. I will say up front, as Gary is going to talk about in much more detail a bit later on, that this is an EPD that is valid for the United Kingdom. In today's presentation, I've used CIBSE TM65 ANZ methodology to substitute the A4 module from this EPD for my presentation today. Another couple of things, the reference life cycle of this EPD, 22 years. Now, if you really love your VRV system and you really maintain it, which you definitely should, you'll get to 22, might be a bit less, particularly if you have changes in the building use over that time. So just keeping in mind that we need to consider that life cycle carefully. So when we look at the data of the EPD, you can see that B6 operational energy is the biggest portion of that pie. And now Daikin put this together. They don't know me, they don't know my building, they don't know how it's going to be used. So in this presentation, I'll talk a little bit about how I go about calculating that B6 energy use. But for the purposes of today's presentation, we're just essentially taking that out of the EPD, and you can see that it's modules A1 to A3 upfront manufacturing, and then modules B1 and B2, which is effectively refrigerant leakage, that are the key life cycle stages that we need to take care of in this presentation. The other thing to be aware of is that the reference unit for this EPD is 1 kilowatt of cooling. So in case anybody in this room is not a building services expert, that 1 kilowatt of cooling capacity represents the building, how much cooling energy the unit can output if it is running absolutely flat chat in the middle of peak summer. Don't get confused, that kilowatt has nothing to do with the amount of electricity going into the unit. That is 1 kilowatt of thermal energy that the unit can output. So that's really important. I will say it is the single most useful unit that they could have chosen as the functional unit, and you'll see why in just a second. What it does also do, though, is emphasise one of the really key ways that we can reduce embodied carbon in building services, and that's by reducing the kilowatt capacity that we require of heating and cooling services. So how do we do that? Well, facade shading. And so I'll jump into the facade section of the presentation. I do want to give a quick shout out to Pete and the Apex Facades team. There we go. Popped his mugshot up here in case it turned up and anybody had any data quibbles that they wanted to check with the team. But I'm really grateful to Pete and the team for pulling this information for me. What we've looked at here is 2 facade options. One that is just a standard curtain wall that does not have any external shading, a comparison case that has a 600 mil deep external horizontal shade. Now, I've got A1 to A3 data here. We're assuming that for those 2 comparison cases, the A4, A5, the B modules and the C modules are going to be pretty much the same, with the obvious exception of B6, which I'll talk about. And you'll see that from that data, the embodied carbon cost of my shading is 63 kilograms per vertical facade square metre, with a normal sort of standard Chinese aluminium product. A low carbon alternative, we might get down to about 25 kilograms per metre squared. So these are the numbers that we're looking at in terms of the investment in embodied carbon that we're spending to improve our facade. So if we go on to the next slide, you'll see sort of some numbers here that I've pulled around how we can look at what benefit that gets us, I've just taken a very quick multi-parameter facade assessment for a Melbourne climate, class 3 student residential on an east-west orientation. I've assumed the south facade is unshaded. Now, this facade multi-parameter assessment, which you can see down the bottom, it does a lot of really great things. It looks at daylight, it looks at thermal comfort, it looks at Section J compliance, all sorts of things. But what I'm interested in are the peak cooling, watts per metre squared. So we looked at our EPD, the functional unit of 1 kilowatt. That's the peak cooling, watts per metre squared value that we'll be multiplying out. The other important value, which should come up in a second, is the annual heating and cooling energy, and that's kilowatt hours per metre squared. If we flick onto the next slide, you can see the two values and how they compare. A couple of key things just to pull out here. So for our scenario with a shade, we're got a peak cooling of about 1600 kilowatts. That would go up to about 1800 kilowatts if we don't have our shade. What that means is every value on our Dakin EPD, we are multiplying by between 1600 and 1800, being the kilowatts cooling on our building. The other thing I just want to say about the annual cooling and heating energy, so this is the electricity that the building is using. You can see there's no real relationship between those two numbers. Don't get tempted just to multiply, divide or one by the other. No, they'd have no relationship to each other whatsoever. So just do be careful if you're not an expert in building services. There is also a lot of uncertainty. We're talking about uncertainty today. There's a lot of uncertainty in when you do a building energy estimation or an energy model. Then you need to do a lot of different scenario testing to understand the different range of uncertainties there. I've left that out in the interest of keeping this presentation to 10-ish minutes, but you would need to engage with your energy modelling specialist to understand the uncertainty in that estimate as well. But if we come on to the next slide, you can sort of see how that looks for upfront embodied carbon. What it means, I'll step on the other side here, is that our facade shading costs 35 tonnes of CO2 over that first 22 years. So what I'm saying is that the embodied carbon we've invested in our shading is not enough to offset our building services capacity over that first 22 years. But obviously we're hoping our building's going to last a lot longer than 22 years. So what's going to happen over that time frame? And as Mark said, grid decarbonisation is what will happen. So you would all be aware that over the last 15 years, Australia's been really, really ramping up our renewable energy capacity in our electricity grid. And you can see the data here showing, maybe if we can just go back a click, it might be a bit clearer. Oh, no, okay, that's fine. Great, so you can see in the sort of solid actual line there that over the last sort of 4 years, we've seen a decline in grid carbon. The dotted line is the 2023 projection for our baseline scenario. And you can see that that grid decarbonisation is forecast to increase and indeed accelerate down to a point where our electricity grid carbon emissions are effectively negligible. What I do just want to say is this is just a projection. Projections may be hit, projections may not be hit. As we learn, if we look back to the same projection that was made in 2020 and compare that to what we actually achieved in that interim time. So just do be very careful with the uncertainty around grid decarbonisation. And if you are looking to look into a little bit more about uncertainty in grid decarbonisation and how that can affect your whole life carbon calculations, if you just come on to the next slide, you can see the Letty opinion piece that was published at the start of last year. And this is a really great primer if you want to dip your toe into some of the uncertainties and things that you need to consider when you're calculating out your grid carbon factor for the purposes of your B6 module. I will say it's very complex both annually as well as hourly. So definitely a good resource to have a look at. But for this assessment, I've taken 4 different scenarios. One scenario that has no grid decarbonisation. I've taken our 2023 projection, and then I've taken 2 other scenarios either side. And if you click on there, you should be able to see the comparison of those charts come up. So for our test scenarios, the B6 operational energy, you can see with our no shade in blue and our 600 mil shade in green, that there is quite a big impact depending on which grid decarbonisation scenario you choose. So what does that mean when we roll all that up together and consider all of those different uncertainties? Should come up on the next slide, I think. Oh, no, sorry. I forgot this important bit. Obviously, I said up front that our VRV system reference life cycle is 22 years. In our reference building life cycle of 60 years, we've got 2.7 replacements that we need to consider. Sorry, can we go back to the next slide there? Yeah, that's the one. And so that equipment is going to also decarbonise over time through decarbonisation of the electricity grid, the electrification of manufacturing processes, electrification of transport. The question that we need to answer, though, is by how much. The RICS professional statement is absolutely clear. If you are going to decarbonise any one life cycle module, you need to decarbonise all of them. So for the purposes of this assessment, I've said, let's assume that the equipment decarbonises 4 times slower than the electricity grid. And you can see that that makes quite a big difference, particularly when you talk about the grid decarbonisation module B6 and across the other ones there. So now we've talked all about all the different uncertainties here. Let's roll on to the results. And onto the next slide, I've just popped across all of our different scenarios that we've done. I've popped those into a just kind of design explorer tool, which should come up on the next slide. The slide back. This is the one. Yep, terrific. Great. I think my red line might be missing. That's okay. You can see the arrows on the side over here. That the actual result that we see for our central case scenario is actually pretty similar between the 2 different options. There's not all that much difference in the comparison that we're looking at for our central case. But across the range of different potential life cycle stages, you can see that quite clearly the blue option, the option with shade, is likely to have the lower embodied carbon across the range of different scenarios that we're looking at here. So what that tells us is that we can move forward with confidence, knowing that our facade shading has a negligible, if not positive, impact on our whole life carbon perspective across the range of uncertainties we're looking at. So then if we go on to the next slide there, you can see that orientation does matter. If my building was oriented 90 degrees, turned 90 degrees, such that the longer face faced north, it's actually a much more compelling argument pro shade. So please don't walk out of this presentation thinking shades are the best, because they're pretty good, but you do need to assess it for your individual building and really look into this complexity for your individual project in each scenario. And I want to say just one other thing before I pass on to the next presenter. Shading is really important for supporting other things, not just whole life carbon. Thermal comfort, reduced glare, improved resilience in cases of power failures. These could be life or death issues in over the life cycle of your building. So we do want to move out of the data and just make sure we're taking this decision in a holistic way. But for a product that is such a terrific benefit to all of our buildings with a negligible, if not positive, whole life carbon. Oh, sorry. Keep going, sorry. It is a really good investment for our building. And then the other thing I just say is that there are so many other ways that we can reduce embodied carbon in building services that don't have trade-offs elsewhere. So that's definitely the other thing to consider. And so I'll pass down to Melbourne, where I think Andrew is ready to present. Thanks, everyone.
Okay, so I got that one. Structure only. G'day. Everyone can hear me okay online? Hands up, thumbs up. Great. Hello. Hi, everyone in Melbourne. Thanks for that, Jen. Really great presentation on the design aspect of impacting building services, and certainly the smaller the capacity of HVAC in general, that has huge implications for the life cycle embodied carbon. So appreciate that you've come to a presentation on building services and you've heard about shading and the impact. The interrelation is really important. I am from AG Coombs Advisory, part of the AG Coombs group. And so today I wanted to share a little bit on I guess, some of the practical opportunities on the contracting side of installing services. And I know that when we talk about building services in general, embodied carbon, EPDs, TM65 calculations, oftentimes we instantly go to the technical challenges that are involved. I think certainly those of us who are engineers and designers understand how valid those are. But I guess in the sort of spirit of optimism that Jeff definitely brought to our working group and wanting to honour that, really wanted to just touch on some of the practical opportunities that exist in our industry. And a key theme of what I want to talk about is that reducing embodied carbon in MEP very much is aligned with embracing circular economy principles. I'm sure most of you in the room are familiar with the concept of moving from a linear take, make, waste style economy to one in which we, in a circular economy, we maximize the value of resources on a planet which inherently has finite resources. And, the important theme, which, is obvious in many ways, is that embracing circularity inherently, in many cases, in most cases, reduces embodied carbon. But importantly, it also has other material benefits. And that's what I really want to focus on. As I understand, being connected to the contracting world, we need to be able to identify the commercial opportunities as well in embracing circular and in reducing embodied carbon. And so I just wanted to touch on a bit of analysis that was done by PwC a couple of years ago, which was trying to put some quantities to the economic opportunity of going circular and reducing embodied carbon. They had a look at the most effective strategies the Australian economy could use across various sectors to reduce, adopt circular principles. They looked at various sectors, they looked at the built environment specifically, and they identified these high priority opportunities. There's a huge economic benefit to be gained over the next 20 years should we fully embrace these principles. And I wanted to touch on modular construction, off-site prefabrication, as being one that has so many opportunities within building services. And, that's what we're here to talk about today. So the figures up there are relating to the opportunities across the built sector as a whole. But I wanted to bring it back to a discussion on building services. And so I wanted to sort of present some opportunities on what prefabrication of MEP modules, so mechanical, electrical, plumbing, what building services prefabrication opportunities there were to reduce embodied carbon. So just looking at some really practical examples here, some of these are sort of more analogies than things that are necessarily being fully leveraged right now. But one concept which I think is really important to understand is material nesting. So when a job is prefabricated offsite, it provides the engineering team with the opportunity to model all of the elements of a job as one. So the material, say for risers, mechanical services risers, all that steel would be nested together under a single model, and an optimized laser cutting regime developed so that it will minimize the amount of offcuts and wastage that would occur against a scenario where steel members are considered individually and cut individually. So what we have found is that this could typically reduce wastage quite significantly, less than 5% against what might be something like 10 to 15%. And then anecdotally, what happens on site is typically there's greater wastage that occurs. And what's really important as well is that the accurate tracking of the amount of wasted material on site, just by virtue of how stick build or traditional build projects go, is that in an offsite facility, you have much more control over the material that comes in through the door and what actually gets engineered. And so there's some great opportunities there. The second opportunity I wanted to touch on relating to secondary steel and supporting steel for services, when we're looking at long reticulation pathways for pipework and ductwork, when you multiply out great lengths of this material for a building, we have the opportunity with additional engineering resources to eliminate oversizing of structural members. So One thing that you find in a lot of traditional builds, support systems for duct, pipe, and so on, they're sort of improvised as they go. Site teams make decisions, and they often use conservatively sized steel members, sort of heavy fixings to support material. And they do so because they don't have the engineering to know what is a smaller size material that will support that kit. And they do so, they improvise that on a service by service basis. So there's no usage of multi-service utilization of the same support. And again, as I mentioned, on site, when that material is constructed, there's more barriers to how accurately the wastage is tracked. It often isn't. If you compare that to a scenario where we would construct a module offsite, you know, there's a big perception, I think, with prefabrication that the structural frame that is used to transport that module and put it in place is definitely an additional material and an additional cost. Whereas in our experience, that actually isn't the case. We often find that the material is it's no more than what would be taken to support that material if constructed in situ. But importantly, because it's engineered, it's very visible, right? So it's a very visible element, and a lot of engineering and thinking goes into making that as lean as possible. And so what we're also able to do with proper coordination is actually have dual use of that steel, which is really important. And I'll touch on that in a moment. The other thing that's really important is this concept of design for disassembly. So being able to effectively recover the resources at the end of life means that if we're making decisions to potentially bolt instead of weld, we can make those engineering decisions and drive that, have more control over that in an offsite facility, a dedicated facility, than if we're relying on on-site sort of impromptu installation. And again, I go back to that topic of accurate wastage tracking. I think our industry is going to just need to understand the numbers first, like the real numbers first, before we make meaningful reductions. We can take those actions, but I think there's some opportunities for additional reporting that can be done with offsite fabrication. And then finally, the topic that I sort of alluded to is avoiding duplication of structural members. And so got a couple of examples here. This is from a recent health project, hospital project that we were involved in. And the roof plant modules there, we were actually able to coordinate with the roof structure. And so the supports were integrated directly with the roof structure. And what that meant was meant we didn't need to install support platforms that would ordinarily be installed in that case. So early coordination is what gave us that opportunity there. This is also a sort of prefabricated modular heat pump array. And so what you see there is not only it has the integration of services with that structural steel, but we also have the integration of access platforms and ladders supporting columns and handrails. And so that's all a single unit, which you can see that was just craned into place. Now, I think that there's further opportunities to reduce the steel in these cases, but the engineering offsite is what would allow us to coordinate and do that. Here's another example of a multi-grade services module where you have mechanical services with electrical service cable trays attached to the same structure. And it's a little bit hard to see, but on the right, you actually see the top part of the structural of a wall that was purposely integrated with the supports of the services. So this actually just avoided the dual use of support structure that would ordinarily have occurred. So that's just a really quick overview of some of the prefabrication opportunities. I only have a couple minutes left, I think. So I just wanted to highlight a couple of other sort of key areas that I think are important. I haven't got a lot of time to talk about refrigerant. It's highly important to this equation. I think most of us in the room, though, are familiar with the design considerations around specifying sort of low GWP or natural refrigerants where the solution allows it. The design practices of reducing refrigerant charge by not oversizing MEC plant, and Jen's presentation on how facade shading would impact that is part of that equation. There are installation considerations as well, you know, how we install pipework, whether the brazed versus flare connections. Maintenance regimes are really important. good maintenance regimes can ensure that circuits are not overpressurized, which could lead to sort of little leaks here and there, and making sure there are good practices to recover refrigerant at the end of life cycle. But a really important point is refrigerant top-ups over that plant life cycle are really important to understanding the whole of life carbon aspect. Those are going to be stored in an asset or information register somewhere, and we need a way to be able to convey that information to the asset team, and so that we can understand more broadly the whole of life impact of those assets. And so I think another really important point for all of us in the room is to advocate for digital technology. A big theme around building services is that the accurate data for embodied carbon of services is still rapidly maturing. We need more EPDs. We need more CIBSE TM65 calculations to provide us that information. But whilst that market is maturing, it's really important that we advocate for the data ecosystems of our built assets to be ready to take that information on, and importantly, to be able to convey that information throughout the building's life cycle, from design and construction, but through to the asset management team. So often information is there, it's rich at the design stage, but then the asset management team does not have that information that should readily be available, or the two disparate systems aren't able to talk to each other. And so there are things that we can do to get our house in order, so to speak. We don't need to wait for the data to be perfect before getting our asset labeling structure, asset syntax that is used to communicate between different data systems to make sure that that information is properly conveyed, and that we can actually have better data on true life cycle emissions for plant. And an important point to convey is that digital technology, it enhances the value of the asset. A building is worth more money with stronger sustainability credentials. You know, Neighbours Energy has proven that. But increasingly, the ability for asset managers to operate that building efficiently and understand the embodied carbon in their plant and have that information will improve the value of that asset. So that's a really key point. And, you know, the last point, you know, we're here in the Aurecon offices, there's a lot of consultants and designers in the room. I just wanted to emphasize from the perspective of contracting, what you specify is so important. You have a lot of power in what you put in a specification. When that comes across the desk of an estimator and a contracting company, when they see clauses that are asking for information, even just asking for TM65 calculations to be done, leave aside needing to necessarily reduce those at this stage. That gives sustainability advocates like myself just more impetus to be able to commit more resources to doing those calculations. You know, Coombs has started that task, and I just want to, you know, leave you with a sign of positivity. The first few subcontractors that we asked when we started looking at CIBSE TM65 calculations for projects that we had built, so we're looking at it retroactively. We're trying to get some numbers around the embodied carbon for ductwork, reticulation, pipework, insulation. We reached out to a couple of our subbies, so Kavanagh Industries, they do a lot of our ductwork in Sydney, and Mulgrave Insulation, they do a lot of our insulation products for duct and pipe. We're working with them. They put their hand up readily because they understand where this market's going. They're ready to provide that information. We need to demonstrate the demand, right? And so we had builders that were asking to work with us to do that. We're working with Slattery Carbon Planning. The QS Slattery have a carbon planning division, and they can provide some sort of like third-party numbers around TM65 calculations as well. So they've been really helpful in that. So just putting up our hand to say, you know, the contracting world is ready to do our part and to advocate for providing information in building services. And with that, I'll say thank you. Thanks for your time. And I think now I'll be passing back to Sydney, where Gary will be presenting from Dakin. So thank you. Look forward to the discussion.
Well, good evening, everyone. It's nice to see everyone here and online. My name's Gary Knox, and I'm from Dakin. I'm one of the engineers at Dakin. I'll just make a short introduction of Daikin. Globally, we're the largest air conditioning company. We have net sales of the order of 29 billion US dollars, with over 100 production bases and sales in 170 countries. And I'm one of 88,000 employees. So if we can go to the next slide, I'll start to look at some of the what's actually in the box of an air conditioning unit. This here, what you see is a ducted air conditioner, a split, with an indoor unit towards the lower left-hand side and an outdoor unit. This is actually the spare parts exploded diagrams. Now, there's lots of parts. There's hundreds. And some of these are more, here, there's some more complicated parts. For instance, we count as one, the fan motor and the compressor. But inside the fan motor and the compressor are even more parts and made of more different materials. But in reality, most of these materials are mostly steel, copper, plastic, aluminium, and electronics. If we go to the next slide, please. So this is a wall-mounted air conditioner with the indoor unit on the left-hand side and the outdoor unit on the right-hand side. The one that's in the spare parts list is actually a single split air conditioner for Australia. We actually looked at another example. It was a VRV unit, a wall-mounted indoor unit only. Of that wall-mounted indoor unit, we found 209 parts. There's 19 basic materials in that bill of materials. And across the unit, there were 62 different suppliers of all these parts. So it gets rather complicated. Now, if you have a look down on the left-hand side, there's a document that is available. It's actually been made in Europe and by appliance manufacturers, so it's not just air conditioners, but they were looking at the e-waste stream. So you can start to see some of the materials that are in an air conditioning unit is predominantly steel, 45%. Next is copper, 21.9, plastics. And even the aluminium is actually rather small quantity, as well as the electronics. So next slide. So where do air conditioning units, chillers actually come from for the Australian market? Well, air conditioners are mostly manufactured in Thailand for the Australian market. So from the MEPS database, which is a government online database, you can see some of the top brands and where those air conditioners are actually made and imported from. Most of the major brands have Thailand, some in China, some in Malaysia. But if we start looking at the Comtrade data that the UN publish, most of the air conditioners from Oceania come from Thailand. Almost $1 billion US dollars from the Asia region. China is second. That's about 300 million US dollars. But when we start looking at the other countries, it's rather small, only 160 million. And those other countries include regions such as Europe and the US. But now when we start to look at, for instance, dividing it into unitary product like split systems and the like, and chillers, we can start to see that the unitary product, most of it comes from Asia, 87%. There's some local manufacturers. They can locally manufacture in Sydney. But very little comes from Europe or the US. So our major influence for product in Australia is from Asia, as we are part of that region. Chillers is different. A great number of chillers come from Europe, followed by Asia, which is mostly China manufacturing, and North America. To put this in some sort of context of volume, about 90% of the value of the market is in the unitary product. Only 10% is in chillers. So that also adds to the understanding of, well, it's mostly manufactured in Asia. In terms of importation, the larger importers, they ship directly from the manufacturing base to each state, capital city, and distribute by road from there. The smaller importers, they tend to ship to one location or one or two locations and distribute nationally from there. So for instance, either Sydney or Perth for distribution bases. The local production, for instance, our facility in Sydney, we ship nationally by road from what we produce in Sydney. So if we can go to the next slide, please. So we're starting to see some EPDs being produced by Dakin out of Europe. This is an example of an EPD that came out of Europe. It's the one in Jennifer's presentation. We can start to see what the impact is, and mostly it's in the operational energy use, almost 94%. Second is B1, which actually happens to be refrigerant leaks over the lifetime of the product. And the raw materials is a close third at 2.4%. We can see a range of materials there, but 86% of the materials is basically metals. And the functional unit on this EPD is to produce 1 kilowatt of cooling or heating. I've highlighted some other points there. This is an R32 unit, and it also talks about which the energy efficiency calculation is based on the European regulations and standards. I'll talk about that in the next slide. It's specific to the United Kingdom because they're using the emissions factor for electricity at 0.32 kilograms of CO2 per kilowatt hour. Jennifer mentioned a reference lifetime of 22 years. If we can go to the next slide, please. So looking around on the internet, I've found 3 different databases or schemes for embodied carbon. The one that Dakin is using is PEP Eco Passport, and I believe they're using a company called One Click LCA. I found an EPD that was produced for an air conditioner by EPD International, and I found a chiller. It's actually a Dakin chiller that was certified by UL Solutions in the US. But what I've found rather striking about these 3 different EPDs is the product category rules or product specific rules, and they turn out to be quite different. So when we start looking at the scope of the Eco Passport is very broad. It seems to cover a great range of products. The EPD International PCR is only for air conditioners or heat pumps less than 12 kilowatts, and the one from UL Solutions was water-cooled chillers. But importantly, the functional unit is different. In terms of PEP Eco Passport, it's 1 kilowatt of heating or cooling, and that's very familiar to me for an air conditioning manufacturer because that's how you size an air conditioner. When you specify it, it goes into a building. And the rating of kilowatts of cooling or heating is very common. You'll find it is the #1 rating. But when we come to EPD International, they're using something that's rather strange to me. It's 1 kilowatt hour of thermal energy exchange with the building, which is 1 kilowatt hour of cooling or 1 kilowatt hour heating. Now, I've never seen that published by a manufacturer. When we start to think about kilowatt hours, we think about the kilowatt hours of the electricity that's used to power the machine. but not necessarily the kilowatt hours of what comes out, the output of the machine. So it's rather strange. US, 1 tonne of cooling capacity, that's pretty much kilowatts as well. Can be easily converted, but US uses a tonne of cooling capacity. The coverage across there, passport one's Europe. EPD says global, but I've got a question mark on that because they're using European regulations for energy efficiency. UL Solutions says global, but they're using ASHRAE and AHRI ratings, so that's pretty uniquely to the US in a lot of ways. And that takes me down to where we start to look at the standards for energy efficiency and operational use, and well, you can see that they're all different as well. Lastly is the refrigerant leak rates. Passport specifies a fixed 2% leak rate. EPD and National, well, it's not specified, so I guess it's left up to the manufacturer to choose what it is. And the UL, the EPD I've seen there actually had a refrigerant leak rate of 0.5%, but that seemed to be an assumption made by the applicant. So I find that this is going to be rather something that we have to work on because it really means it's hard to really evaluate the impact and make a comparison about similar products. Next slide, please. So talking about energy efficiency ratings, I'm quite involved with energy efficiency ratings. I'm making a small comparison between the European rating system and the Australian rating system. So when you do a calculation to work out the efficiency, in Europe it's SEER, or Seasonal Energy Efficiency Ratio, and SCOP, Seasonal Coefficient of Performance. We use a different measure, which is called TC, Total Cooling Seasonal Performance Factor, and Heating Seasonal Performance Factor. They worked out to different standards. For instance, in Europe, it's a European standard. We have a European regulation, Lot 21. Australia, we have our own regulation. It's the GEMS Act. And we use the international standard, the ISO standard. We have different testing points. And we also have different ranges of zones. For instance, in Europe, we have a cooling climate zone only, just for one. We have 3 zones for heating. But in Australia, we have 3 zones for cooling and 3 zones for heating. Most importantly is the ranges of the temperatures that are used. Europe uses a lot colder temperatures and a lot colder temperatures in their bin hours or the hours of use. And they use a lot more heating than what we do here. We're predominantly a cooling region. So it's going to make it quite challenging to compare or the energy efficiency, which is actually rather dominant in an EPD. Next one, please. So I'll just have a little bit of a word on emissions factors. We've seen the UK emissions factors for electricity was 0.32. We do have emissions factors for electricity that is published by the Australian government under the National Greenhouse Accounts Factors, and they change as we decarbonise, but we have a different emissions factor for each area of Australia. The one that I'm mostly interested in is the annual leakage rates. We have a very good understanding of the leakage rates across different equipment in Australia, and they're published by the federal government. And they're quite an important part when you're starting to work out what is the embodied carbon of the refrigerant leakage. So on that note, I think I have reached the end of my discussion. We go to the next slide to say thank you, and look forward to having a chat at the panel.
Right. Gary, thank you very much. A lot of detail there, a lot of complexity in the machinery that you're producing. So thank you for shining a light on that. I might ask our panelists to come up to the Melbourne guys, maybe get together. Here in Sydney, we'll get together. Now, I hope I know quite a few people have jumped on Slido already, which is fantastic. And that will really inform, well, makes my job a bit easier, really. Now, I've never done a bi-locational panel discussion, but you guys, the Melbourne guys are physically, the screen has you to my right. So if I'm looking that way, you'll know why. And questions haven't on the Slido don't say who they're for. So I'll ask the question and I might then seek volunteers to who wants to put their head up and take that one on. So first up, should NPV, net present value principle, be applied to carbon emissions or embodied carbon? If so, do we agree? How do we agree on the discount rate that should be applied by industry?
I'll put my hand up first because I did upvote this question. I thought it was a great one. Look, I think the answer is yes. I think it is important to consider that the carbon we spend today, we don't get back, and that we need to consider that that has a much bigger impact potentially in the context of the environment over the course of the nominal 60-year life than carbon that's potentially spent at the end. How we arrive at that factor, though, is something that I think we're going to need to discuss as an industry and come to a appropriate estimate. I don't even know where to begin, if I'm perfectly honest, but I think it's a great opportunity for us to collaborate and really talk through that issue.
Okay, thank you. Did the other panelists in Melbourne, have you got a view on that?
Just to say that there is a lot of complexity in the measurement. We had a meeting yesterday, I think, at ASBEC, looking at our embodied carbon project there, and someone mentioned that for infrastructure there's also enabled emissions. So what you build, does it enable more emissions? I think there's just so many different factors to consider that we need to do the numbers. But I guess point I come back to is we still need to move. We've still got to keep moving forwards. So yeah.
Okay, thank you. Hey, next question. And this one might be for Gary. With you've mentioned refrigerants a couple of times. How much does refrigerant leakage contribute to the embodied emissions of building services compared to all the different components?
Okay, let's see if we can try and quantify that. Basically, the way I tend to think about the emissions from refrigerants compared to the products, about say 90% is going to be in the operational energy use. We've got like a 410A refrigerant that's going to be about say 9%. R32 is probably going to be about 3%, and then we start looking at materials that are going to get down to around about that 2 or 3% when we look at it. So I will stress that that will make energy efficiency of the product the number one priority, as the current situation is with the emissions in the grid, followed by refrigerant leaks, followed by materials itself.
Okay. It's interesting, isn't it? I said at the beginning that MECLA is all about an ecosystem, and I think this is proving that there just aren't any silver bullets for embodied carbon. There are so many components that come together literally for your products, but in terms of the value stack of where does the carbon come from, it's not just thought this, you're done. There are many factors. Another question. The European auto industry has laws around availability of replacement parts for maintenance. Should the building services industry have a similar policy? Maybe as a product supplier, Gary.
Yeah. We have like policies or thereabouts for I think 8 years from the time that a product is finished its sales in the country. I'm not too sure about the actual laws and having a figure there. It mostly comes under provisions of the ACCC, and ACCC has been looking at rights to repair and the like in recent years. So it is something that's under discussion in Australia.
Okay, thank you. Melbourne, any thoughts there? OG Coombs, have you got a position on that?
Yeah, I think my comment's a bit more of a general one, which is that I think consideration of embodied carbon is going to, in general, put an emphasis on HVAC service, preventative service and maintenance, and add another element to the importance there that previously might have only been in the consideration of FMs to maintain the functionality of that plant. But, you know, Gary even just touched on the impact of having like a fairly high GWP refrigerant and what leakage could mean. Right now, the consideration in reality, refrig techs will recharge that equipment, and just the cost borne by OPEX is not as big of a deal as it should be in terms of the broader impact. I think maintenance companies like our service division as well need to also contribute by providing real world data on how active maintenance will change those numbers. Because I think realistically, it's going to be so important to not just have cost being the only thing driving this, but have real data being pulled through as to what the impact of leakage really is on whole of life carbon.
Great, thank you. Another question, should B6 operational carbon be included in an EPD, or should it just focus on embodied carbon? And Jen, I knew your hand was going to go up.
Yeah, I have quite a strong opinion actually. And I would say it absolutely, yes, it definitely does. And the reason for that is that we can't always, when we're comparing one product against another, we can't always go and do a whole energy model and then a whole comparative assessment and then tell all our friends about it. And we do need that information to be prepared in a way that's consistent and that's representative of how it's going to be used in Australia. Yes, we can do better, more bespoke assessments, you know, on a case-by-case basis, but that's no reason not to have a reasonable number on the EPD to start with.
Any other thoughts, Melbourne? No, okay.
Well, the initial thought, sorry, Hudson, is, you know, absolutely support that, Jen. It is kind of confronting though when you see that initial number, isn't it? It just looks like it outstrips embodied carbon so much. And I think the decarbonisation pathway probably just needs to be made more clear to understand that there's a real pathway for reducing operational carbon. And in general, our industry has been so focused on reducing operational carbon. NABERS ratings now for energy, like the average rating's up around 5-star. They didn't even, like originally when they created NABERS, they weren't thinking that 6-star was really achievable, and now 6-star, they had to create a new star for it. So I think it's great that we have that comparison, but hopefully the number, which looks really high for B6, doesn't put people off understanding how important it is to start thinking about embodied carbon. Makes sense.
Please.
Yeah, may I just speak about some other things? It's very important to not trade energy efficiency for something like refrigerant. This is a very important principle that's part of the Montreal Protocol, the HFC phase down, and the Kigali. It's also important in the UN. So trading to a lower GWP refrigerant but sacrificing energy efficiency, you're going to have a negative effect.
Again, it's a whole of systems thinking rather than just one component of a problem at a time. When is embodied carbon modelling necessary? Jen, I know you're going to, let me keep going, but I know you're going to want the microphone. If we know shading has multiple benefits in a project, do we really need to model the embodied carbon? Would it change our design?
Yeah, I think that's a great question. I think it does merit thinking about, and where I want to get to is a point where we are considering it up front. I gave a deliberate example where I'd pulled shading off the south. I've worked or heard about a project where there was a push to put shading on the south. Now, from an embodied carbon perspective, that's absolutely nuts. Do I need to model it? Probably not. But if I did, I'd have some pretty good numbers to look at. So I think, yes, there's a time and a place for modelling, and that's early and upfront. And the quicker that we can get this information onto our projects, I think the better, even if we do need to sacrifice a little bit of accuracy to get there.
Thank you. This might be a question for Mark in Melbourne, and it may be a definitional question. Why did you assume other industries will decarbonise 4 times slower than the electricity grid decarbonisation?
I think that might have been from Jen's presentation in the numbers. I think, I read it as a conservative estimate, but maybe Jen can.
Sorry, Mark, if I've thrown you a hospital pass when Jen's sitting right here.
Yeah, so I mean, to answer that question, 4 times was a estimate. It was a number, it was a guess. I think it is a bookend. It is probably pretty optimistic to think that we are going to be able to decarbonise building services 4 times slower than the grid. I think it's going to be much slower than that. But, it was just for the purposes of providing an illustration. I think it's another great opportunity for collaboration to start looking and forecasting that. And certainly if anybody has done that, I'd really want to hear about it.
I think from a MECLA point of view, one of the reasons we set up was, the Green Building Council and the movement around that have shown, after 25 years of particularly looking at operational performance and operational emissions, that the combination of more efficient services, better demand management, demand response, and a decarbonising grid, that curve is dropping down. But unless we act on embodied carbon, that won't change. The proportional impact of embodied carbon in buildings will increase, just because it is hard and needs to be challenged, needs to be tackled. So I think that's part of the answer as well. Okay, next question. Does use of low GWP ODP, we like acronyms in this discussion, don't we? Does the use of those refrigerants align with increased scrutiny on PFAS, forever chemicals, and what should change to open the market to natural refrigerants?
Well, that's a very good question. Okay, well, when it comes down to refrigerants, there are safety considerations involved, and different systems can have different refrigerants. For instance, in the industrial space, there is a lot of natural refrigerants present. This is now coming into the commercial refrigeration space, say for instance in supermarkets we see CO2 systems. But when it starts to come to the HVAC area, there's a lot of consideration about safety in regards to the occupied space has got end users that are unaware of the safety considerations, whereas in an industrial area, all the employees of the industrial site understand the safety very, very well. So when it comes to a natural refrigerant in somebody's house, we have to take a lot of extra precautions in making sure that the refrigerant choice is the right choice.
Mark, as someone with ERA, what's your perspective on that?
Yeah, I think we need to take a broad view on refrigerants. So I think we talk about carbon blinkers. I think we sometimes get GWP tunnel vision and sort of say, it's all about, how much global warming does the refrigerant create when it's released to the atmosphere. It's important to remember that there's embodied carbon in the production of refrigerants, and we don't have very good information on that at the moment because they're quite often proprietary processes, and there are upstream and downstream byproducts involved in the production of especially synthetic refrigerants. And I think that's an area for investigation. Some of the feedstocks that are used to create fluorinated refrigerants are actually very powerful global warming potential gases. Some of them are ozone depleting gases. And we also know that there are concerns about when the refrigerants break down at end of life, that they're breaking down into types of PFAS, forever chemicals, as you mentioned. So I think there's definitely it's something that we need to look into, and not to sort of just go, oh, it's all about the GWP. There's more to it than that.
Terrific, thank you. Okay, how is reference equipment life calculated? Is it based on real-world average lifespan or manufacturer-backed recommendations? Gary.
Honestly, I don't know where the actual years, the reference lifetime, comes into the EPDs. I do kind of like, how do I explain it? A unitary split system has got a nominal lifespan of about 13 years. They work it out in Dakin. They work it out as a 30,000 hour lifespan of the compressor, and when applying a like a amount of hours per year for a residential application, they come up with a number of about 13 years. But other publications, whether it's, say, for instance, through ASHRAE or even ERA, I think maybe that's 15 years, but 20 or 22, that's it's come from, they come from the EPD creators. I'm not too sure why, but that's what they come up with.
Terrific. All right, thank you. Now, looking at time, we have more questions than we have time to answer them, which is good in terms of demonstrating engagement from the audience. It is bad that we are going to have to call it quits. Let's ask one more question, and then I have, I'm going to ask each of you to a call to action. So, it's hard choosing the last one. There are so many good questions. Okay, so let's bring it to what's coming in Australia soon. Can anyone please share opinions on how building services will be treated under the upcoming Neighbours tool? Mark's nodding.
I just think that's one of the things that we're really curious to see. We know that that Neighbours is going to start with a system that is realistic and that can be trusted, and that means it's not going to look at the whole building in terms of all services and you know, fit outs and stuff like that. So the answer is that you're not really sure at the moment. We've talked about maybe that it might sort of go to what they call cold shell level, and then over time expand to other building services. But really excited to see the tool when it comes out in June.
Thank you, Mark. And I will say, MECLA is engaging a lot. We heard earlier this week, late last week, from James Elks at the part of the Neighbours tool, and so the engagement is ongoing. There's no, big green stick from government. It really is co-development. Look, we're nearly at time. I want to know, look, this is really complicated. Both of you had slides with great detail. I'm going to start in Sydney and then go to Melbourne. But Jen, what's the one thing that you can do as a professional to drive a reduction in embodied carbon in your work?
Yeah, I think the main call to action is really to get started, to get cracking. Look, there's complexities. There's a way through navigating those complexities. There's data gaps, sure, but there's ways to get through that as well. So really do get started. You'll identify the things that you don't know, and then in a couple of years' time, those data gaps will be filled, and you'll have an ecosystem that you can really rely on. So get started today.
Okay, I think that we really should be looking at PCRs, what the product category rules are, and start to define what they are in Australia, so that we can have EPDs that are relevant to our region.
Okay, thank you. Andrew.
Yeah, thanks, Hudson. I think I touched on a couple of points that I'm going to continue on. I think the contracting world can provide some just simple, practical examples of reduced embodied carbon. So I'm going to continue to advocate, particularly in the areas of prefabrication. We have a facility, and so I'll be working with the leader there to look at the material that goes in those doors and that gets shipped out to site, I think by having that data and having some metrics, we can start to have our own internal tracking and to also contribute to the market in connecting with our subcontractors in providing the calculations needed for TM65. I think that'll be really useful for the industry. Actually, it is unknown amongst a lot of people in the industry how much embodied carbon is actually in all the duct and pipe and steel in services, and it's more than you think. So that's what I'll be involved in.
Mark.
Yeah, so kind of coming back to that idea of circularity, I think part of it is just looking after what we've got, right? So what we've created, let's make sure that it works for as long as possible in the best way possible. And it just is such a simple thing to do is improve maintenance of building services in our buildings. It's kind of low-hanging fruit. So that's definitely something that ERA is advocating for. And it's not really a technical problem. If anything, it's more of a workforce regulatory problem that we just need better controls in place to make sure that what we've got in our buildings is working as well as possible. And probably, you know, not so much the kinds of buildings that we're sitting in today, but when you get to those sort of mid-tier buildings where there's really not much care taken, there's big opportunities for improvement.
Okay, now I think it's only fitting that the last word goes to our absent friend Jeff. He, of all people, submitted questions ahead of this event to be asked to the panel. So I have to admit that's just giving me goosebumps, but I would now ask each of you, and sorry to the fastidious timekeepers in the room, we're going to go over. This is the question from Jeff, and I don't do accents, so I won't try to do an Irish accent, but with love, here is a question. What does the panel think the predicted timeline will be for the ready, cost-effective availability of green steel for the supply of low-carbon ductwork and HVAC equipment manufactured in Australia? Mark, can I go to you first as a confidant and fellow traveller?
Yeah, and I know that one of the last occasions that I was with Jeff, that, you know, this was a topic that came up. But look, it's a really difficult area, low embodied carbon steel. It's one of those wicked problems. But I guess this is the kind of thing where, you know, are there other options we can look at? Are there other types of ductwork systems? I guess, you know, what can we do in our space at the moment is probably look at, you know, design things. Yeah, I wouldn't be able to put a time frame on it, unfortunately. So, yeah.
Any others? Our working group on steel will tell you that it's incremental, it's hard, that the sector is, particularly in Australia, is a technology taker. But Andrew or Gary, I know early on you were saying there's so many material inputs, so many suppliers, but steel, copper and aluminium were some of the biggest. So steel?
Okay, so steel, I've been reading a report from the IEA, the International Energy Agency, which is made up of the governments of the world. Now, they've got a roadmap for decarbonisation to net zero. So the way that they've got their roadmap really starts to come into green steel in the 2030s. Right. So we're quite a way from the green steel, but it will progress to 2050 from there. So I haven't got great news there, but I am taking in the answer from the IEA.
Okay. Well, I think Jeff would want us to keep pushing. So let's keep pushing. Let me thank Aurecon emphatically. The generosity of hosting us in 4 sites, to have the IT, which has been pretty seamless, to have us in 4 sites is remarkable. If I can stuff up IT, I will, and I couldn't. So thank you to Aurecon, David, Law and Peter for your introduction and for welcoming us. Mark, Jen, Andrew and Gary, for your expertise, putting yourselves out there, open to all of those questions. Thank you very much. We will keep collaborating. We'll keep sharing information. Thank you for joining MECLA this evening. If you're at one of the physical locations, I believe there are drinks and nibbles to be shared and conversations to be had. For now, that's it. But thank you very much for joining us, for your contributions and for your expertise. Thank you, everybody.